Okay, everybody, we're going to start up again here. Kostas is going to go through a few more slides, and then Tony Leboissetier is going to talk a little bit about the ocean. So let me share my screen again. And I'll let Kostas take it away.
Thanks, Mike.
Sure.
So let's start now looking the details into the run deck, and we start from the very bottom, how you control the timing. I mentioned before the break about this input Z section, that it is the very few last lines of the model of the run deck. And you have, oops, can you go back one?
Sorry, just a minute. Trying to, some reason. There we go. Sorry, go ahead.
So there are, I have three colors here, and I just realized that I have to apologize for the potentially colorblind audience here. The year I, month I, date I, and hour I in green is when the nominal years that you start the model. In general, and for all planetary cases that we have done, this is only an index. It can be anything you want as long as it is an integer number. So the year can be 1. It cannot be 0, if I remember correct. The year can be 1 and can be any 4-digit, up to 4-digit value that you want, unless you turn on some explicit configuration in the model that allows for more than 4 digits. But in any case, it's just a number. So it says here 1897. It doesn't mean that this is simulating the year of 1897, or it's just a counting. And then the months go from 1 to 12, this regardless of what kind of planet you have. If you have a planet with a 6-day orbit, you still have 12 months in the definitions here that Tom Clooney will discuss about the calendaring tomorrow. And then the day is day 1. And you need to remember that depending on the planet rotation, not rotation, orbit, you might have actually rotation. Yeah, you might have more than 1 day. So you always start from day 1, obviously, but the last day of the month is not necessarily 31 or 28 or 30. Again, Tom Clooney will go through that in tomorrow. The key thing I want you to remember is that the year I is an index, month is always 1 to 12, date is always 1 to whatever makes sense in the model, in the current planet, and hour is always 0 to 23. Then we have the year E, and all this line that you see in red that says when to stop the simulation. It can be any time you want into the future. And then we have this exotic line in purple with that says I start equals 2, and then again some numbers. I start equals 2 is the way to tell the model I will be providing you some initial conditions files and use those to start the simulation. An alternative is I start 9 and I start 8. These are the 3 flavors that you will be using probably. And we will get to those later, maybe tomorrow. But the important thing for now is that this 2 means I will be providing you an atmospheric initial conditions file, AIC, a ground initial conditions file, GIC, and if relevant, an ocean initial conditions file, OIC. And you can see those listed in your randex already. Then I is just the seed for using the random number generator into the model that is related with clouds. So it doesn't matter what number it is, it can be anything. It just changes the seed of this random number generation. And if you want to make sure that your simulations are exactly comparable, you should have the same I across your simulations. If you want to make simulations that do differ despite the their configuration being identical, simply changing this will change the results just by adding some numerical noise. Then year E is when to end the simulation, month E when to end it, date E when to end it, and hour E when to end it, but not the simulation itself, the initialization of the model, because the model cannot start its regular cycle with from the initial conditions. It does that, it initializes itself, the whole state of it, and then saves the state on a restart file. And then you run the simulation from that restart file. There is a way to skip that, and you can do it, but probably for supercomputing reasons that you do not have unlimited time, you have batches of like 12 hours for 24 hours, depending on the computer. You really need to be able to write into restart files occasionally and then continue the simulation from those. So the way we do it is that we start from the initial conditions, we save the restart file, and then we do the standard simulation. And you will notice here that the default is exactly 1 hour after the year I line. So all the green numbers are the same with the purple numbers, except the last one, hour E. So the initialization of the model is what we call it the setup hour, because it lasts an hour. But again, this is nominal. It can last any integral number of hours you want. You can even go all the way to the end of the simulation if you want. But you need to understand that this comes with a price. If, for example, your simulation is extremely long, or your simulation is, or you are limited with CPU time. But the standard way is this: you define year I to something that you want to start your model, you define year E to when you want your model to end, and then you define the I start equals 2 line to be 1 hour ahead of the year I line. And we also have a line in the run deck that says master year equals 1850. This is inheritance from the Earth model that essentially it says we want to continuously simulate the year 1850, and we need to be able to use the greenhouse gases or emissions or anything relative to that. For planetary applications, this 1850 is a number that you should be using, or it can be any number you want, as long as you provide the necessary information to the model for that nominal year. It doesn't mean that it has to be 1850. I mean, you can provide CO2 concentrations of like whatever you want, 20% in the atmosphere. Earth never had that atmosphere, most likely. So, but if you put that value in the 1850 line, then of the input, then you're good with the conditions you want. So it's just a year. And one thing that we are not using in the planetary simulations, but the ability to use it is there, is to set master year equals 0. If you do that, then the years that you have defined in the input Z section above start to make sense. They are not just indices, they are the actual years. So essentially, in the example that you have here, if we have master year equals 0, then the first year of the simulation will tell the model, let's take master year equals 1897. When the year ends and you go to the second year of the simulation, you tell the model implicitly, master year equals 1898, etc., until you go to 1910. So in essence, the simulation is a transient simulation with numbers changing from one year to the other, and the model is able to pick up those changes along the way. Again, I don't think that anybody of you will be running transient simulations in that sense, but it is a capability that is there. So, I mean, we have here listed that we can run the first hour of 2 run decks. Do you want to do that, Mike, or you want to continue?
I think we should just go on because we'll do some of that tomorrow. Chris will do that sort of stuff.
Yeah,
for us.
and we can also do that at the end of the day today in the Q&A session.
Yeah,
so
and everyone should have already done actually the first hour of the.
That is also true. Yes. So okay, let's go to the next slide then. Okay, so back to those 4 randex that I was mentioning earlier. I already said what they mean, so I'm not going to repeat that. Remember how you did it before coming to this meeting. You cd to your dex directory, you run the command make randec, and then run src equals, you pick one of those names, depending on which one you want, and then run equals any name that you want. We use here the same prefix _test, but it can be literally anything. It can be your name. It can be anything that makes sense to you. And picking a right randec name is art that you will master down the road, because it's the way for you to quickly separate experiments. And you see the randec name, and then you immediately know which exact experiment this is. So you will develop that, and it's a very personal thing. Then, especially for the first time that you are using this one template, you need to run this command that starts with .. /exec, etc. Essentially, it says, go to our server and download the input files that are relevant for this randec and save them in the directory that is listed here on the right. It can be any directory you want, essentially, but it has to be the one that you defined in your .model ERC. If you do the same make randec command multiple times to create multiple randecs using the same template, you do not have to modify to run again this get input data line. But if you start picking a different randec that you have never used before, then you need to repeat the get input data command to get the files that are missing. The ones that you already have that are common, for example, topography is common throughout the top 3 randecs. But if you run this get input data command again, it will only search for the new files that you do not have based on the new randec that you have just created. And then after you have created your randec and you have made any changes you want in it manually in this P1SOM40_test, you can change anything you want in there that makes sense to your experiment. Then you do the make, so which essentially compiles the model. We do have a make clean here at the front. This is good practice in case you are doing major changes or you are changing important things like compilers or libraries, or you have changed the modules in the model. But when you are doing routine compilation, it is a step that you can skip, especially if you are not modifying the source code, but you are only creating new randecs, for example. But it is generally, if compilation fails, this is a good first test to see whether something is left over that shouldn't be there. So you do a make clean and then you run the compilation again. If you can do it every time, it will slow you down though if you have several experiments that use the same source code, because it will have to be compiled all over from the beginning. In any case, no matter how you compile, you have created the setup. This is the make -j. -j stands for use parallel compilation. So the compiler will pick the maximum number that makes sense for this compilation and based on your computer's architecture. And then, so it will be it's the fastest way to compile actually. And then you say setup, which means compile the model and at the same time create the output directory with the main scripts that I will be using during runtime. And then when this is done, you run the last command on the slide that says run E, the run you want to start, and then -- restart, which says use the I_start = 2 line as the end time, and then -np and the number of processors you want to use. If you do not have MPI, you should be using 1. If you do have MPI, you should be using whatever makes sense to you, but not greater than 44 for our M40 resolution. If you use more than 44, the model will crash with a cryptic error message that might look confusing. Just never exceed 44 unless you with the M40. Okay, let's go next. Running with tracers very quickly, because I know that most people will not be doing that, but it is something that you need to know of. We do have the carbon bond mechanism 4 chemistry in the model. It's abbreviated CBM4. It's a way to simulate present-day Earth with a very small number of tracers, but enough to be able to capture the tropospheric ozone production and destruction and some other key gas phase components. We also have a KPP, which stands for a kinetic preprocessor implementation under development. And this will allow to create some very different to modify the chemistry very easily, or even create a completely new one. But for now, if you want to do gas phase chemistry, you need to read our paper, the 2017 model description, that tells you about the limitations and the bounds you need to pay attention to. Then for the aerosols, we have the one moment aerosols, which just assumes that there is one size of aerosols and then it has some certain composition. And the size can be different per aerosol component, but it will be one size per component and fixed in time. We also have matrix, which the acronym is pretty long. I don't remember it by heart. And it is a model scheme and resolves the aerosol mixing state and also the aerosol size distribution. So sizes do change. It is much more expensive than the OMA scheme. And then we also have Thomas, which is a sectional model, but I'm not going to discuss about that too much. We have not used it a lot, and it is an abandoned configuration for Planet 2.0. So probably nobody will ever use that. So let's go to the next one. Then when you have a new planet, you need to think of two major things in terms of composition. One is the major components in the atmosphere. For present-day Earth, nitrogen, oxygen, argon. Then you need to think of the trace gases into this atmosphere. And if you are doing non-interactive atmospheric composition simulations, essentially the only thing you care about is radiatively active components. So the question is whether you have methane, whether you have ozone, and then whether you have dust, sea salt, or any other aerosols. And you need to remember that if you have aerosols, they might be affecting clouds, and this is something that you might or might not want in the model, or you might need to take into account in any case. So you just need to build up your atmosphere based on that. And there are many other greenhouse gases that are supported in the model, and there is a way to create new radiation tables to take into account gases that we do not have right now, or some relative proportions that are different from what we have right now, and you need to calculate more different radiation tables to be more accurate. I don't remember if I think that Eric will discuss about that tomorrow, right?
Yes, he will.
Yeah. Okay, so I'll leave it to that, and let's go to the next one. Okay, so before passing to Tony, that he will speak about the ocean, a few other important flags and the files. The reason, if you look at after you do the make setup, if you look into the output directory, which is soft linked in the dex directory, you can find that there is a file that is called I. It is an uppercase I. This is essentially the same thing with the run deck with two important differences. One is it is not listing any of the source files that have been compiled. It only lists the input files that the model is having and the parameters that you are passing through the run deck. The other important thing is that it does not have any comments. It is just a stripped down version of the run deck. It is essentially the file that will be read by the model to do anything that you want to do. And why I mention this, because it's really important to know that there is a way, and there are cases beyond just trying to hack the model. There are legitimate cases where when one might want to change some configuration as the model runs. So you stop the model, you pause the model essentially, and then you want to change something of your initial settings. And there are limits on what you can change during the model simulation, but let's say you want to change something that is changeable. So you do not go in the run deck to do that. You always go in the I file to do that, because the run deck will not be read by the model. The I file will be read by the model. Another file to keep an eye on is a file called lock. This is created when the model is running, and it is there to ensure that you will not be launching the exact same simulation at the same time by accident, which avoids, of course, overwriting your own files. And you don't have to worry about that unless the model crashes. If the model crashes and you fix something and you want to continue the simulation, this log file might or might have not been deleted. So if it has not been deleted, you will get a message from the model that says, hey, I see a log file. So is the model running? If it is not running, so you check whether the model is running because you might have done some typo. So if the model is indeed not running and it's the correct one you want to continue, you go in the output directory, you delete the log file, and you submit the job. Then there is another, the way to debug the model. And the way to debug the model is what we call you compile it with traps. And the flag is all uppercase compile underscore with underscore traps equals yes. And you put that at the end of your make command. So it is make -j setup run equals whatever your run idea is, and then compile with traps equals yes. And that enables additional flags that do slow down the model, but they are checking things at runtime. So the model might compile, but might still do stupid things because you made some mistake or something is missing, or you moved the model in a place where it has never been before. So this will help you debug the model if it is crashing at runtime, not if it is not compiling. And then if you enable the extra flags, that says -O0, then this disables optimization, which is something you don't necessarily need to do, but we have it there as an option for in case you want. And then the -G enables some debug stuff. You need to remember that you must do make clean both before and after. If you do not do make clean, then the model will be compiled with traps. Only the files that have been modified since last compilation will be compiled with traps, and the others will not. And if the model is crashing in one of the other files, you will not get debug information. So always make clean. And after you are done with the debugging and you've fixed everything and you want to do production run, do remember to run make clean again. Because if you do not remember to do it, and you run the model in production with traps, then the model will just go very, very slowly because of those extra sanity checks. There is nothing going to be wrong with the output. The model will be slow. And then in case you want to stop the model, there are 2 or 3 different ways to do it. The simplest one is you run this command that you see here from your dex directory. // exec / /sswe uppercase E, and then you run ID. And that sends the signal to the model that you request the stop. It does not stop the model instantaneously. As the model runs, it periodically checks, very frequently, periodically checks in whether a flag has been raised to stop the model. And when it sees it, it saves the model output. It saves the model state in one of the restart files and stops gracefully. This might take a little bit, depending on the speed of your computer, depending on at which point you say the model to stop. It might take anything from a few seconds to a few minutes. But in general, so it's not that you will instantaneously see the model stopping, but you will see it, and then you will be able to do whatever you want with that. And okay, let's go to the next one. I think I'm done. Yes, so I don't have anything else for now, so we'll pass it to Tony, and I will be continuing later.
Great, thanks, Kostas. That was fantastic. So yeah, our next person is Tony Leboissetier, and he's going to tell you a little bit about the ocean component of our model. So take it away, Tony.
Thanks, Mike. Morning, everyone. So I'm going to walk you through all the different flavors of oceans we can run with ROCKE-3D, and depending on your research interest, you may want to run a standalone atmosphere with a prescribed ocean, or a standalone ocean run with a prescribed atmosphere, or even a coupled ocean atmosphere run. So basically, we have 4 different options to run the ocean. The first one is the prescribed sea surface temperatures, where you run the atmosphere and there's no ocean modeling per se. You just provide the atmosphere with a file that has all the sea surface temperature for each grid cells at every time step. And this is useful, for example, when you know your sea surface temperatures for the whole duration of your simulation, like, for example, modern Earth. This is also quite computationally cheap when compared to the fully coupled ocean, dynamic ocean, and atmosphere. Now, the second kind of ocean run we can perform is what we call a Q-flux run, or a mixed layer run, where instead of using a dynamical ocean, you're just going to use a thermodynamical slab ocean, where you compute the heat content Q, hence Q flux, of the mixed layer of the ocean, and the heat exchange between the atmosphere and the ocean mixed layer. And so for exoplanet runs, we usually don't have horizontal heat transport between grid cells. But if you know the horizontal heat transport, you can prescribe it for example, for Earth-like simulation. This is also quite cheap when compared to our third option, which is the fully dynamic ocean coupled with the atmosphere, which is the most realistic. But in addition of the atmosphere, you have to solve at each time step all the ocean quantities, the momentum equation, the ocean dynamics, for example, the vertical and horizontal mixing, the tides, etc. And finally, the fourth option that we have at the opposite of the spectrum is the standalone ocean, where you're just using the ocean module of ROCKE-3D with a prescribed atmosphere. This is useful if you're only interested in the ocean, or if you're trying to debug something with the ocean. For Earth, we're using the core files. It's a series of files that simulates the atmosphere at the top of the ocean. It's basically the temperature and salinity at the surface of the ocean, the wind speed at the surface of the ocean, the radiation, and the precipitation. And to give you an idea, this is usually the cheapest of all of these runs for the when the ocean is involved. If you're running a 4x5 model for 1,000 years, if you're using the fully coupled model, it will take you around 18 days to run 1,000 years. If you're just using Standalone Ocean, it will be under 2 days to run 1,000 years. So, Mike, if you could skip to the next slide. It's quite educational to put two different run decks side by side. So Mike and Kostas described these run decks before. The one starting with a P1 is a run deck for the fully coupled model with a dynamic ocean, and the one starting with P4 is a run deck for the Q-flux ocean. And if you're using the diff command, which is very useful when you compare two files, you can see, for example, that there's a whole host of subroutines present in the P1 run deck for the dynamic ocean that basically calculates the whole ocean dynamics that are totally absent from the P4 run deck. If you skip bit down in your run deck to the parameters section that Kostas described, you will see different parameters and options related to the ocean. For example, the K ocean equal 1 indicates to your model that there's an actual ocean to compute at every time step. If we were using our first option from the previous slide, the prescribed SST, then we would use K ocean is equal to 0. But there are a lot of other options and parameters that you can use at runtime, meaning after compiling your run, you can play and activate options like the use of tide, the bottom drag, the drag at the bottom of your ocean, the mesoscale, diffusivity, etc. I'd also like you to pay particular attention to three very important files for the ocean that are listed here. The first one being the one labeled OIC, which is for the initial condition of your ocean. Basically, you're telling ROCKE-3D what's the initial state of your ocean, the mass, temperature, and salinity for every cell. And there are two different formats that you can use for OIC, what we call the native format for ROCKE-3D, where instead of the temperature using the enthalpy, and the salinity is expressed in units of PSU over 1000. You have to be careful if you're using the native format. In version Planet 2 of ROCKE-3D, you will have the option of creating a simpler OIC file where you can use just the temperature in degrees Celsius and the salinity in PSU, and there will be a dedicated subroutine that converts your OIC file into the native format. The second input file that you want to look at is our ocean topography input file, topo_OC, that basically has three two-dimensional variables. The first one, the ocean is the depth of the ocean for every cells in meters. The second one is the atmo, that's the height of the land cells. And finally, F ocean, that's the ocean fraction, which is either 0 if it's a land cell or 1 if it's an ocean cell. Finally, O straits is a text list of all the straits that connect to ocean masses through land cells. And it's basically a list of for each straits of the coordinates of the straits, the width of the straits, and the depths of the straits. one quick tip also, if you're running a planet that doesn't have land mass at the South Pole, and Mike touched upon this earlier in his presentation, you might want to go in the source directory, in the model directory, and look at the file called oceandin.f and make sure that the variable J10, which represents the lowest latitude at which the ocean dynamics are computed, is equal to 1. That's also something that you probably won't have to do for version 2 of ROCKE-3D. And finally, the next slide for the ocean is a quick overview of the updates coming. If you can skip to the next slide, Mike. One of the things that Mike also described is that soon we're going to be able to run deep ocean. So the current version of the ocean model is what we call a hydrostatic model. But when you want to model deep ocean, and by deep ocean we mean ocean depth on the order of 10 to 100 kilometer deep. I remind you that on Earth, the ocean is on average between 3 and 4 kilometer deep. And so quasi-hydrostatic ocean model entails both a full treatment of the Coriolis force, which is not present in a hydrostatic ocean model, and a relaxation of the shallow water approximation. So we make these updates available for Planet 2 soon. And that this will be important if you want to model a planet. Like, for example, we think that some of the planets in the TRAPPIST-1 system might have a very deep ocean, or even in our solar system, icy moons like Europa in orbit of Jupiter, or Enceladus in the orbit of Saturn have beneath the thick ice shell 50 to 100 kilometer deep oceans. And also a quick word of some updates coming from the sea ice, because the sea ice is part of the ocean module. We are improving right now the radiative transfer through the sea ice, and that will make the sea ice thermodynamics much more realistic. That's it for me. Back to you, Mike.
Okay, great. Thank you, Tony. So does anybody have any questions on any of the materials we've presented so far for either Tony or for Kostas? You can unmute if you want to ask a question.
If no one else is going to jump in, I have a question.
Sure.
I know that you showed in an earlier slide that the Q-flux and the fully coupled oceans came out to pretty close equilibrium for the overall planet temperature. Has anybody done a apples to apples comparison about how the Q-flux and the fully coupled ocean work for per grid cell temperature and rainfalls? How much fidelity do you give up by just going with the Q-flux?
Well, I think it depends completely on the planet. So if you look, for example, at our Proxima Centauri b paper, we do compare the Q-flux to a fully coupled ocean, and there are some substantial differences. I don't know so much about the Earth side of the house. Maybe Kostas could comment on that, but most people on the Earth side of the house are not using Q-flux oceans so much anymore. Kostas, do you have anything to say about that?
So it all depends how you construct your Q-flux fluxes, essentially. So for Earth, the reason why the Q-flux model was even designed was because there were no dynamic ocean models back then. So if the Q-flux ocean was constructed in a way that brings the atmospheric circulation, that couples the atmospheric circulation and the heat transport with some ocean heat transport too, that makes sense for Earth. If you go away from Earth, or even if you stay on Earth but just change the period you are studying by like 200 years, the heat transport is different. So it is really important to know how exactly to create it. If you take, so the way that people are doing things right now in the planetary community is, of course, we do not have sea surface temperature measurements on any other planet. So we do not know how to construct a proper QFlux file. So what happens is that people are either saying, we will be using the QFluxes of Earth and hope it's good, or we will be using QFlux of 0, which is no heat transport because it is 0 is as plausible as a number as any other number. So, so then when you will be comparing that with the dynamic ocean, which actually resolves things that are relevant to that planet, whether it does it correctly is irrelevant, but it is resolving things depending on the planet's state. And then you should expect that you will have differences between the QFlux and the dynamic ocean in that other planet. I don't know if that answers your question.
It does. Thank you, Kostas.
Okay, great. Any other questions before we take a break? Leah?
Hello.
Hello.
Hi, sorry about that. I was looking at this about the ocean model. If you were interested in simulating, I guess, not early Earth, but essentially a time scale of Earth, how much computational power would it be? Would you recommend the smaller ocean model, or would you recommend something if you were trying to do, or the fully coupled?
Yeah, it's a good question. I would say that in the community as a whole, most people are limited computationally. They don't have the computational resources to run a fully coupled dynamical ocean model. So most people in the exoplanet community are running QFlux models, either, as Kostas said, with this QFlux set to 0, or the QFlux set to Earth values using an Earth continental distribution. Or there are other ways to set the QFluxes based on some more primitive equations that people have attempted in various publications over the years. So most people are still using QFlux models in general. And I think that the papers like the one I showed you show that in certain regimes, the QFlux model does a fairly good job. So it really depends upon your science. It's hard for us to give you advice for a given scenario what the best choice is. What I would recommend, unfortunately, is to dig into the literature and see what people have modeled. Often the problem with that, to some degree, is that they don't often compare the validity of their QFlux assumption against a fully coupled ocean. That's the negative, because again, people are computationally limited. But I would say that if you're not sure, you should always try to run a fully coupled ocean if it's possible, if you have the computational resources. And otherwise, you go for what you can model, basically.
Right, but with the computational, I'm assuming that using the fully coupled, that takes a very long time from what I'm understanding.
Well, it depends. So it depends on how long it takes you to get the ocean temperature to be in equilibrium with the atmospheric forcing you're putting upon it. One way that we have gotten around that in our group, and other people have attempted the same, is to use a shallower fully coupled dynamic ocean. So maybe instead of making your fully coupled ocean, say 5,000, as much as 5,000 meters deep, for example, for the Earth, you could make it, say, 1,000 meters deep. Now, it will not capture all of the dynamical processes. You may not get, for example, the Atlantic overturning meridial circulation correct and things like that for an Earth to get, a true fidelity to an Earth model. But it will probably give you fairly accurate results for another system for which we do not have constraints on, what the AMOC, as I just described it, actually is in your particular planet. So often people say in aquaplanet scenarios, they pick shallower oceans to see how the model responds to that. So in our Proxima Centauri B paper, we actually have an example where we picked a much shallower ocean and we compared it to what it looks like in a deeper ocean. so that people could have an idea of how the model responded to those kinds of changes. So again, look in the literature and see, for your given, scientific interest, if other people have done something similar, and see if their approach is the one you want to take.
Another solution is also using, it's a bit tricky, but using the standalone version of the ocean, which is much faster with the right forcing for the atmosphere to reach equilibrium for the ocean. And once you have an ocean in equilibrium, then you can couple it to the atmosphere.
Thank you.
You're welcome, Ellie. Hopefully we have a slide a bit on that tomorrow. So if, as Tony's saying, if you're making a new planet and it's very similar to one that we have modeled previously, we do, in some cases, have the checkpoint restart files from the end of those runs that you can use to bootstrap a new run. And so you'll be much closer to equilibrium if your forcing differences are not too distinct between what you want to do and what we've done previously. So we'll try to touch on that a bit tomorrow.
Definitely. Yeah, no, not necessarily a new planet, but I am interested looking at paleoclimatology of Earth and somewhat maybe like a time series of sorts with that, with this model. But I don't know. But yeah, thank you. I appreciate you guys taking the time to answer that.
No problem, Leah. Glad to help you. Any other questions?
If I can build off of your suggestion about the shallower oceans, is there a way to create the OIC file for that fairly easily if we want to have a paleoclimate continental configuration?
Yes. Sorry, Mike.
Go ahead, Tony. No, go
ahead.
ahead.
No. If you need help creating your OIC file, you can always get in touch with me or Mike. But I have a bunch of programs already written to create the OIC file where you can specify temperature, salinity, and it will compute your net CDF input files.
Magnificent.
Yeah, and again, Stephen, like we've been saying, if you can find a simulation that's very similar to what we've already done, say in terms of the depth of the ocean and the continental configurations and things like that, it's best to try to bootstrap off that. And we actually have a project which is going to be wrapping up this year, a 3-year funded project, where we're going to start posting a lot of the boundary condition files for some paleo Earth scenarios. So once those papers come out and those boundary condition files come out, hopefully people using our model in the community will be able to use those to kind of bootstrap things.
Sounds like it's going to be a great year for ROCKE-3D.
I hope so.
Keep my fingers crossed.
Okay, well, we're scheduled to take a break about now, so I think we should go ahead. We'll have another session this afternoon for about 45 minutes. Then we'll have another 15-minute break, and then we're just going to have an hour of Q&A, and you can ask anything that you're interested in from the tutorial today. So if you didn't get a question in now, you can get it in then. Go ahead, Ricardo. What's that?
Is it better? I have a question about the global. So the fully coupled ocean circulation model. Is it better for the Q&A later, or should I ask it now?
Yeah, we'll have plenty of time this afternoon if it's okay.
Okay, yeah, I'll do it then.
Okay,
all right.
Thank you. Yeah, well, Tony will be around. I'll be around. Igor, everybody will be here, so we can take any questions then. Okay, great. So we'll see you all at about an hour and 15 minutes. Enjoy your lunch if you're on the East Coast, your dinner if you're somewhere else in the world, or your breakfast, depending on where you are. And we'll see you soon. Thank you.